Welcome to the session 3 of Unit 1 in Digital Signal Processing. In this session, let us try to understand the mapping between analog frequency to digital frequency. Before going towards the mapping, let us try to understand the representation of continuous time and discrete time sinusoidal signals. A simple harmonic oscillation is described by the continuous time sinusoidal signal as x sub a of t is equal to a cosine of t plus theta, where t runs from minus infinity to plus infinity, where a is the amplitude of the analog signal, is the frequency in radians per second, and theta is the phase in radians, whereas the subscript small a is used here for indicating the analog signal. Instead of ohm, we can use the frequency capital F, generally expressed as cycles per second or hertz. So the ohm and capital F can be expressed as ohm is equal to 2 pi f, and this relation, if I'll put in the expression 6.1, I can write the analog signal as x sub a of t is equal to a cosine of 2 pi capital F t plus theta, where t runs from minus infinity to plus infinity. Similarly, I can express the discrete time sinusoidal signal as x of n is equal to a cosine of omega n plus theta, where n runs from minus infinity to plus infinity. Here, capital A is the amplitude of the discrete time signal, omega is the frequency in radians per sample, and theta is the phase in radians. Small n is the sample number. Instead of omega, if I use the frequency variable small f, generally expressed as cycles per sample, the relation is omega equal to 2 pi f. If I use this relation in the expression 6.4, then discrete time signal can be represented as x of n is equal to a cosine of 2 pi fn plus theta, where n runs from minus infinity to plus infinity. So this is the way we can represent the continuous time and discrete time sinusoidal signals. Next, let us try to understand the mapping with the help of the sampling of analog signal. There are so many ways to sample an analog signal, but we will limit our discussion to uniform sampling. This is described by the relation as x of n is equal to x sub a of n t, where n runs from minus infinity to plus infinity, where x of n is the discrete time signal obtained by sampling the analog signal xa of t every capital T seconds. The time interval capital T between the successive samples is called as sampling period, and its reciprocal, that is 1 upon T, is called as the sampling frequency, generally expressed in terms of hertz. The variables T and N can be related as T equal to Nt, as I know that T is equal to 1 upon Fs, capital T is equal to 1 upon Fs, I can write the variables T and N as small t is equal to n capital T, which is equal to n upon Fs, because capital T and Fs are reciprocals of each other. To establish a relationship, consider an analog sinusoidal signal as x sub a of t is equal to a cosine of 2 pi capital Ft plus theta. This is a representation of analog signal, and I can show that analog signal in this way. If I'll sample the analog signal periodically at a rate fs samples per second, then after sampler I can have a discrete signal in that The dashed signal is nothing but x sub a of t, that is the estimate of analog signal, while x of n is equal to x sub a of nt is nothing but the sample signal. So we can write the sample signal as x sub a of nt is equal to x of n, which is equal to a cosine of 2 pi capital F nt plus theta. So here this small t is replaced with small n capital T. That is this relation. So the same expression I can rewrite as a cosine of 2 pi capital F small n upon Fs plus theta, because t equal to 1 upon Fs. So the sample signal I can express finally as a cosine of capital F n upon capital Fs plus theta. So let me erase these notations. Okay. So we were up to this point x sub a of nt is equal to a cosine of 2 pi capital Fn upon Fs plus theta. This is the expression for the sample signal. And x of n is equal to a cosine of 2 pi Fn plus theta, where n runs from minus b to plus b. This is the expression for the discrete time sinusoidal signal. If we compare these equations 6.6 and 7.5, then we can write as small f is equal to capital F upon Fs, or we can write as omega equal to ohm into t. The ranges for the frequency variables of capital F or ohm for continuous time sinusoids are capital F runs from minus b to plus bt, while ohm runs from minus b to plus bt. The ranges for the frequency variables small f or omega for discrete time sinusoids are small f runs from minus up to plus up, or omega runs from minus pi to plus pi. The equations 8.1 to equation 8.4 represents the mapping between analog frequencies and digital frequencies. So these are the equations I have brought in this slide for the reference. Yeah. If you compare the equation 8.1 and 8.2 with equation 8.4, we can write as f is greater than or equal to minus fs by 2 and less than or equal to plus fs by 2. That is, capital F is running from minus fs by 2 to plus fs by 2. Or if I talk in terms of ohm, then that ohm is running from minus pi fs to plus pi fs. From the relations derived above, we can observe the fundamental difference between continuous time and discrete time signals in the range of frequency variables. Periodic sampling of continuous time signal implies mapping infinite frequency range capital F into a finite frequency range small f. Capital F is running from minus infinity to plus infinity, while small f is running from minus up to plus up. That's why it is the mapping of infinite frequency range into a finite frequency range. From the equation 9.1 One, we can also comment on the maximum frequency of the continuous time signal as Fmax is equal to Fs by 2. As Fs is equal to 1 upon T, I can write it as Fmax equal to Fs by 2, which is also equal to 1 upon 2T. Or Ohm max is equal to pi Fs, which is again equal to pi upon T. It means that if I'm sampling a continuous time signal with a sampling rate Fs, then continuous time signal can have its maximum frequency equal to Fs by 2 only. That's it for the today's session. Keep learning. In the next session, we will try to understand the sampling theorem. Thank you.